Okay, we start now. So our distant participants have some problems, technical problems. However, we don't have any. So we start now. Any questions or remarks or suggestions? Then we start with a summary of lecture 1. So I'm going to discuss 2 points. Just restore some notations. Naively, we are going to study polynomial equations over k that is going to be fixed. I mean, the notation is going to be fixed, the ground fields, and solutions are going to be considered just individual solutions, not the tuples of solutions, but individual in K capital that will be variable. So this is the first point we discussed in a straightforward way with some important questions, examples to which we are going to return. And then there was a mistake about quadratic equations. Such an elementary subject as quadratic equations in characteristic 2, and thanks to yes. Do I pronounce you correctly? Right. Okay, now just forget everything that has been said about that. I'm going to prepare lists of exercises, so you'll have all the correct formulations then. The subject is elementary, and a bit exotic, but quite important. So that's for the lecture 1. Any questions or remarks about that? Good. So, very briefly, at the end of the previous lectures, I pronounced something about what we are going to discuss now. We are going to discuss a central question about the subject of algebraic geometry. As I was saying briefly, we are going to consider 3 points of view. The first one is the sets of solutions of polynomial equations. It was mentioned before, the subject is not so simple as it might seem, so naively. It is going to be the set of usually we suppose here that the ground field is algebraically closed, and we are going to consider the subsets of the affine set, affine space, sorry, and capital, and it's important, or better, in the subsets of the projective space. Well, soon we are going to introduce the Zariski topology, perhaps remind what Zariski topology is, and as far as I remember, the participants usually, as a rule, know what all these words mean. Please note the font I'm using. There will be 3 kinds of X's, and the bold will be used for algebraic varieties. So this is the naive point of view. So usually when people are told that algebraic geometry is just dealing with the solutions of the systems of polynomial equations, no questions arise. However, we are going to consider almost the same, perhaps I even copy it, and say that we are going to consider something that is called in the same way, but let's develop a categorical point of view on this subject. Basically, we are going to think seriously about what is a polynomial ring, and well, in some sense, what does it mean to substitute say number in the place of variable. It is classical, but as I'm going to explain, not very well defined, and in any case, not the classical and standard notations for all these subjects are not really rigorously defined. Maybe I start explaining this with the details from the naive point of view. So suppose we are having k polynomials of the variable. Here are small x's. In fact, we are going to consider perhaps also two fonts for that. Let's think for a while. What are these x's? The correct mathematical answer is that they are just the generators of this algebra. All of them just generate a free commutative algebra over the ground field. And when we consider the system of equations, and say that we have found a solution. Usually what you see in any box is that sometimes x sub 1, x sub n, sub n are solutions if something strange like f, all the f sub I of x1, xn is 0. Yes, you are told things like this. When something like this is meant, then x sub i's are no more the elements of the rings, but just numbers, the elements of the ground fields. I think that this kind of inaccuracy is dangerous, at least for the building rigorous foundations of algebraic geometry. So, well, I'll suggest something close to this, so that we do not go too far from the standard notations, but it is not going. My temporary suggestion is not going to be quite comfortable. So let us recall ourselves what is a polynomial. What is a polynomial? Here it is convenient to not to restrict ourselves by the finite number of variables. What is a polynomial? Now I introduce the second x, a polynomial with a set of variables. I use the capital X, the X, not simply capital, but really of larger font than this one. Usually, let's know that usually X is a set of standard elements, but As I said, first of all, we should not suppose that, a priori, we do not suppose that this set is finite. And perhaps some of you remember the construction of the algebraic closure of an arbitrary field, where at some point we use for the set of variables all the irreducible polynomials over the field. Yes, this is the Emil-Artin's construction of the algebraic closure. And next, even when x capital is finite, sometimes its elements are not numbered naturally, and we do not need this numeration in the categorical definition of the polynomial. Now, Now we define a category. So as for the standard notations, again I suggest the huge ring of polynomials. We know that it's ring, so I omit it. Nomials in X is large X. We denote as K with this great brackets, and use just the abbreviation. Sorry for these boring maybe details, but I think they are really important. The abbreviation is that when we are going to work with the standard set x sub 1, x sub n, we omit some brackets and denote it in the traditional way, as we did that before. So it is the thing we are just going to define. Perhaps nothing to ask about at this point. Now I reproduce the definition that I found in the first editions of Lang. Def from, one of the most classical algebra books. Search Lang algebra, but I'm afraid that it is there only in the early editions. I looked briefly through the last editions and sorry, just didn't find it. Maybe I was not attentive enough. But we'll develop our own notations that are convenient for algebraic geometry, at least for plugging the numbers in the place of variables. So we introduce so any x is any quite an arbitrary set. Sorry, I don't remember whether we have agreed about some style of categorical language. Perhaps we did, yes?
No.
Oh, so I work with the categories as if they were sets, but I duplicate most of the characters. So this is a short way to say that x, this big X, is a set. I cannot use single character like that, because set is not, sorry for the joke, set is not a set, it is a category of sets. And I always use this kind of font for the category. And then we defined, so our main special key is fixed, and that is here is the name of the category of K algebras. I hope nobody needs the definition of it together with its morphisms, yes? Or maybe just to train the notations, I write it down and then erase. So K, the category of K algebras consists of the pairs say A and alpha, where A is a ring. Sorry, I don't, well, may I say just orally that we are going to consider two kinds of rings as everybody, the commutative ones and possibly non-commutative ones. Since the commutative algebra was mostly developed in France after the World War II, I choose the perhaps commutative. Well, I'll just use this. It is subcategory of the category ring. That is, therefore, the obvious definition of the category of associative rings. We'll always consider, I don't write it anywhere, but all our rings are going to have units in there. And this is not complete. Well, perhaps I erase these obvious things. So in this pair, A is the commutative ring and alpha the morphism from K to A. And well, with the obvious now the general convention is that whenever we have two objects of the clear category, then the arrow between them means that it is a morphism in that category. And then, just to define category, a category, we need to define more the morphisms and write it separately. So the set of morphisms in this category from the pair A alpha to the pair A prime alpha prime is just the set. Here we use the usual braces, the set some other letters, say F, A to A prime, such that the diagram like this commutes. again, without special, the default meaning of any diagram is that they are commutative. So I just, well, warm up us a bit to get used to our categorical notations. Any questions about that? Okay, so this is a category you knew very well. This one is a non-standard one. So we put our big brackets, and by definition it is again a pair. What are my notations? Again, the set of pairs A and epsilon. This letter is chosen to use the word evaluation map such that A epsilon, yes, where A is just a K algebra, is a K algebra, may erase the definition of what you all know. And epsilon is a map. Now I use the broken line for the obvious reason, I hope. The reason is that this arrow is not a morphism in any category. Strictly speaking, it is a morphism of sets, but to consider A as simply a set, we need to apply the forgetting factor that would lead us to cumbersome notations. So this is just the mapping of set, and again, obviously, the morphism in this this category. From A epsilon to A prime epsilon prime is, of course, a map. Perhaps I can write it just the same way. It is a ring morphism, K algebra morphism. I hope you understand the difference between what I said first and said after that. It is not only the morphism of commutative rings, but it is over K. So it as it was written there. And of course, there are the evaluation maps, and the whole diagram should be commutative. Now I should find a place to answer this question. Perhaps let this notation survive, and I want to say that K of X is a now I have a language or philosophical difficulty. I don't know to use the definite or indefinite article, a or the, sorry for that, initial object. It is just the initial object in the category we have just introduced. Of course, we mean that, together with well, obvious x to k of capital X. So, my uncertainness here comes out of the problem whether in the category, as soon as it has initial object, is it the only one, or there are many but canonically isomorphic? Let's skip this question. So anyhow, up to the canonical isomorphism, this K algebra, together with the evaluation mappings, is well defined. I'm afraid that this notation is, well, rather abstract for those who see it in the first time, but let's discuss it informally after we define what is the set of solutions of a system of polynomial equations.
I have a question.
Yes, please.
Does the category we defined have a name?
Yes, you mean I've given only the notation, yes? And you'd like a name of it. Thank you, it's a very good question for which I'm not ready. So, it is the categorical analog of the rings of a polynomial. Well, I'm just improvising now, but I would suggest perhaps to call it the polynomial extension of the category of K algebras. And when we say polynomial extension, we use the set of variables as a parameter. Thank you. I didn't know that the people there that are interested in the language, the mathematical language, are among the participants. It's good news for me. Now we answer seriously to the to the question, what is the set of solutions? Now we consider just a subset K of this capital X, or very big, and it's important that the extreme cases are possible. This set can be empty or can coincide with the whole ring of polynomials. And now for K capital, being an object of just being an algebra over the ground field, we define perhaps let's just just underline it and put this K capital as an argument. And then we are going to see that the natural definition is that we consider we use the morphisms in our K polynomial category. In the category we have just defined of what so K of X, and we understand that there is a canonical mapping of the set of variables there, but we use just the ring. We factorize it over the ideal generated by this set, and yes, we put K here. So let's this is a central part of the definition. I box it, and let's work a bit with the corresponding diagrams. So we have our K of X here. Here we have the factor ring, factor algebra. Now we have X somewhere. Here we have a commutative diagram like epsilon here, I don't know, see maybe epsilon underline. It is of course well defined just by the commutativity of this diagram. Now we have K somewhere, and so what is a solution? A solution is, erase it in this in these objects. The mappings of the set of variables are default, but here let's use epsilon, and it is really the evaluation map. That means a solution is the operation when we give the value of all the variable in this field. Here is the naive, we reproduce the naive point of view. By definition, we have a commutative diagram like this, but since this system of equation is satisfied, then all the polynomials from the system annihilate on this epsilon. That means precisely that we have such an arrow, that this evaluation mapping factorizes through the factor object. So this is a long way. Sorry for that. I thought for several years about this definition, and I'm unable to give it shorter. But I think it is a correct one because, well, maybe I won't reproduce it, that otherwise the assigning numerical values to variables just means using some sets of letters instead of other sets of letters. So it is not precise, not rigorous, and I think we stick to this long notation, but we are going to make things much shorter, because now let's think what this underline is. It is obviously a functor. Sometimes I well, to begin with, let me duplicate it. And it is obviously a functor from the category of K algebras just to the category of set. For the time being, we do not supply the set of solutions by any other structure. It can be given the structure of Zariski topology and so on, but the universal understanding is like this. A good question, well, perhaps I formulate some questions and statements after we discuss this definition, if it deserves it. So please, any questions or remarks? So, well, following David Mumford, I'd like to give a question that is perhaps not closed. So, hopefully all of us understand what a polynomial is. Yes, so I raise it. This is kind of tautological. So the most important pieces are here, still preserved. So informally, they just say that we consider the solutions of our system of equations in all the K algebra. So there is a version when K is not a field but Z, then this is just a functor from all the commutative rings to set. So this one also deserves some boxing and discussions, and it just tells us that two things. The first, that maybe the most basic objects of arithmetic geometry is the system of equations with integer coefficients. Well, perhaps I mention the Hilbert's. The Gilbert's 10th problem, the negative solution of which by Matyasevich explains that basically the whole mathematics or the whole mathematics, the results of which can be expressed in terms of algorithms, is can be expressed in the language of systems of polynomial equations with integer coefficients. What we say just that we are, the first thing is that we are going to consider the solutions in all the rings in the world. And the next thing is that this association to a ring, this set of solutions, is an interesting functor with some property. Now I follow Mumford as I promised. Mumford, who called Grothendieck's existence well, maybe not precisely in this form, but well, the question by Grothendieck-Mumford was maybe algebraic geometry just studies the functors of this kind. So there are some functors. The existence problem is characterize them. In a more technical language, the question is what functors of this kind are representable for those who are used to category concepts. Among interesting functors from arithmetic and algebraic geometry, there are representable ones or not representable ones. This is representable by definition. The value of the functor is the set of morphisms. So perhaps the whole characterization is unknown, but I want to mention some natural problem like this. So in particular, I think it is open. At least I have never seen it printed anywhere. You can formulate several obvious properties of this functor, like the behavior with respect to direct products and so on. In the Mumford books about curves on algebraic surfaces, you can find some non-trivial properties of this very functor, but any system of equations defines the the mapping. So Q, well, as I hope to remind you today, one of the most important achievements of arithmetic of 20th century was related to considering the solutions of polynomial equations in finite fields. So a small finite piece of this question is like this. There is a function that associates to any q, well, q is going to be a primary number, as you will see here. So this is a temporary name for some functors we are interested in. Let's suppose that the values on, it can be one of the axioms that the value of such functor on a finite ring is a finite set. Now we consider just finite fields and ask ourselves what are the cardinalities of the value of our functor over the finite fields of Q elements. Of course, what I've written now is just well, not the most natural way to ask about the number of solutions of polynomial equations in finite fields. But I think that this context is a proper one, and as I said, the best achievements of arithmetic geometry of 20th century is about that. At least the dimension, if the functor, double question mark, is of the nature of the system marks, then these cardinalities have the polynomial asymptotics, the degree of polynomial being the dimension of the corresponding algebraic variety. But I think this question deserves just the study from the very beginning. So this is what we have discussed up to now, is the second point of view of what is the subject of algebraic geometry. Perhaps it can be said seriously enough that algebraic geometry studies functors like that. Well, yes, in several versions. The definitions I've given are related to affine varieties. We should set several more words with the homogeneous ideals and graded rings, so that to include the projective varieties, though of course these functors like that, sorry, I didn't say that they are called functors of points. And the brief second answer tells us that this is the second point of view on the subject of algebraic and arithmetic geometry. Maybe I should stress before that the difference is that algebraic geometry usually works over algebraically closed fields, and is interested with the geometric properties of corresponding sets of solutions, while arithmetic geometry mostly works over non-closed fields and rings of finite type. Okay, any questions about this second point of view? Well, no questions. And there is the third answer that certainly should be mentioned and will be important for us mentioned in the modern course of arithmetic geometry. And this is another generalization of the naive point of view related to understanding the arithmetic geometry as the theory of solutions of systems of polynomial equations. So the third point of view we are going to discuss is the Grothendieck's schemes. But perhaps we need some motivation. So, may I ask to raise your hands those who know the definition of Grothendieck scheme? Everybody knows what it is. Okay, so I can be quite brief in discussing it, but I'd like to give an informal motivation of the extending the subject of our study to such abstract constructions. So I'd like to do it informally and a very general tendency of arithmetic geometry. Sorry, we have not elaborated the standard abbreviation for that. So include is to include let's write it like this: systems of equations into families. For example, we have discussed as some down-to-earth examples in the first lecture the cubic surfaces. Then working with some nice of them, we'd like to have results concerning all the cubic surfaces. Now I want to discuss another basic example. Well, perhaps I I'll write it down and ask, maybe all of you know the situation, then I'll have to choose another subject. So I'm ready to call it a basic Example, congru. And please raise your hands, those who know what it is and what is the status of this theory. Oh, good. Well, this is quite a concrete question. I'll write it like this. We return to Pythagorean triangles with A, B, C, natural A, B, C's, and the area S. So, yes, such an S is called a congru. And so a number is congruent if it is a rational number, is congruent if it is the area of the Pythagorean triangle. So it is convenient to consider the Pythagorean triangles up to similarities, and then the congruents are the elements of Q, well, positive multiplicative group over its square. So, this funny question is about 4,000 years, can be considered as the question that is, well, at least 1,000 years old, and it is partially solved. That is, the modern mathematics has the definite answer. However, modulo yes, so congruence, that's denoted as the sets of numbers. It is known in quotation as mark modulo sorry, Svinyatandayer and sorry for escaping. Dyer, I think, maybe you know, the first name is well, the famous person whom I know, conjecture. That is one of 6 remaining millennium problems. Birch. millennium problems. Now I'm going to tell you about the arithmetical geometric part of it, and by the way, when I conclude, we'll have the first arithmetic surface at our disposition. Sorry, I have a special technique to remind it. Look, 1, 25 and 49 is a short progression, arithmetic progression of squares. Now, what are these numbers? They are related to the simplest Egyptian or something like that triangle. And now 1 is 4 minus 3, and 5 is 5, and 49, 7, the square root of 49, well, square root of 1, and square root of 49 is 3 plus 4. That means that if we have it here, we consider 3 numbers. Suppose, well, unlike what you see here, suppose A is larger than B, and then you have A minus B square smaller than what is the next 1 plus 4 A B. In the middle we have just C square, and here we have A plus B square. Yes, so this is the arithmetic progression, as we see, with the difference 4AB. Yes, 4AB is the difference here, and or 2AB, sorry, no, it should be 4, yeah, 2AB, 2AB, and S is a half of AB, so 2AB is 4S. So the question is, which S's are the differences in the short 3-term arithmetic progressions of squares. This simple question is in fact the reformulation of the problem of congruence, and we immediately rewrite it in a more geometric term. May I erase everything else? No question this. So consider x minus s, x and x plus s are squares. Multiply it and get the equation y squared is x squared minus s squared. So I should say that this is the first arithmetic surface. But it is the arithmetic surface not in an obvious way. So perhaps I go up here, and as usually we have to give every equation the name. So this is let it be I was speaking about the families of equations. Here, instead of asking whether a given number is a congruent, we consider them as a family and ask this question about all of them. And sorry, I turned out to be not ready for the name, but let it be the name of this equation, let it be cong sub s. The equation, so the equation is in y and x. Now let's draw. Sorry, I will never distinguish the equation in the form left-hand side equals right-hand side and something equals 0. This is the traditional one. So the left-hand side has the roots 0, s, negative s, now for what we draw here in our language we have a perfect name. As you understand, this is the set cong S of R. Yes, this is a beautiful cubic curve. And then there is an easy theorem. Telling us that S is congruent. Sorry, perhaps I didn't introduce the set of congruents, but let's do it now. Cong, say, in capitals, yes. If and only if the set of rational points on these curves is infinite. Now, this is a popular formulation. It can be a bit shorter. As soon as I ask you, please raise your hands, those who knows what is a rank of elliptic curve over number field. One hand. Okay, so it can be reformulated in other way. So in fact, this is not just a set, but together with infinite points, it is an abelian group, and then its rank is positive. So there is a great industry concerning the calculation of rank of elliptic curves. I'll give all the definitions in all the details perhaps in the next lecture, but for the time being I want to explain, to realize this object as really, as a truly arithmetic surface. So finally we give an example corresponding to the title of this course. This is something like this. So since all of you know what is a Grothendieck scheme, you understand that the spectrum of Z is the set of primes together with the infinite point, together with the infinity. Now it's a long name. Let's use the temporary one, E. It depends on this, but let's remember it. So over 2 we have E mod now I write it like this, over general P, and let me draw it in some symbolic way. We have here, we put here E over F P. Yes. sorry, it's the correct way for us with our notations. We know, just apply what we have discussed in general to this very seemingly innocent equation. That means, given S, we consider some cubic curve, and then, since it is an equation, we'd like to look at it over all the finite fields, this time over field of residues, but please don't think about it too naively, because, well, maybe I draw it in here. We should consider this E over Fp bar over the infinite set, and, well, over here in between we have here E over all Fp to the R. Sorry to write it large. Fp P to the R. So over every P we have an infinite tower of finite sets. By the way, it was written here recently that we are considering that every system of polynomial equations define the functor. The functor, it is not only system of sets. Whenever the algebras sit one inside another one, and in the finite sets of fixed characteristics this is the case, that means that we have the whole system of finite sets. Those who understand the structure of algebraic geometry over finite fields understand that these concrete finite sets are invariant sets of the Frobenius automorphisms and its powers. What sits here is just invariant with respect to Frobenius itself. Up there we see the sets that are invariant with respect to the square of Frobenius and so on. And so on. So this is a system with well, with a complicated dynamical system. And the arithmetic of these curves depend on all these. And here we have E over Q. Finitely, we have E over Q. So this is the first arithmetic surface. Of course, there is nothing special in this very equation of the cubic curve, and we'll discuss the arbitrary cubic curves and the arithmetic surfaces they define. So it's time to stop here. Perhaps one last remark that I can also write down in our today's notation. So by the way, there is a final set extremely useful for all the systems of equations and in particular very useful for these families of elliptic curves, and then cong sub S of C does not depend on S, obviously. Here we can, well, replace X by X over S, and what we have to do to replace Y over perhaps over S to what? To S to 3 over 2. This operation does not exist over rational numbers. Therefore, over rational numbers, these curves depend on S, and this is the nature of the congruent problem. Unlike other families that we are going to consider, the fibers, what is over the points of the spectrum, the fibers are isomorphic over C, but different over Q, yes. So I'm going to stop very soon. I just want to remind you that this example to which we are going to pay some attention was introduced just before reminding you things about Grothendieck schemes, because these relative pictures, like something over something, in a very symbolic way, we should think about this structure as about family of curves over spectrum of Z. And the classical language in terms of well, solutions is insufficient for that. But the language of Grothendieck schemes, together with the Grothendieck's relativistic principle I'm going to formulate during the next lecture, is perfect for considering various kinds of morphisms, in particular the families of curves. So this is all for today. Any questions or remarks? Now, let me see.
What is drawn on the picture? What is this object?
This?
No, the whole picture.
This one.
Yeah.
It is, thank you for a good question. It is just, the drawing is nasty. However, what is meant is the arithmetic surface. So it is supplied with the arrow down. By the way, Grothendieck was the first person who used these arrows, not from left to the right, but from top to the bottom. And we think about it as about curves over every point of the spectrum. This is the arithmetic surface or the arithmetic family of curves. This is what is drawn. So even more symbolic picture would be like that. And well, from the point of view of Grothendieck's schemes, it is really like this, only the base of this family is just the spectrum of Z. We are going to discuss it in more detail.
And the total space is what?
Is just the whole thing here is the subject of our considerations. Matic surface. You could think about it as, to begin with, just as about the union of fibers. But Grothendieck's language of schemes allows us to consider the total space as a scheme. It makes no sense in the classical algebraic geometry. It is not a subset of some affine or projective space. It is an abstract scheme together with the morphisms, the morphism like this. Other questions or remarks?
Two naive questions maybe. First is what is cons derived there? S belongs to cons.
Yes, it is not cons but cong. What I was meaning, thank you. What I was meaning, set of congruent numbers.
Why do we especially care about that equation defining that cubic curve is? What was special about it?
Oh, just because it is related to the what? To this property of a number S that is equivalent to being congruent. The property is that it is a difference of a short arithmetic progression with square members. Like here, it was here, I have erased it. So it's just a motivation to consider some special arithmetic curve. Other questions? Okay, then thank you for your attention. Hope to see you in a week and hope to produce a list of problems, including the promised ones.